Okay, so we define the problem of signal enhancement using multiple sensors with, by applying the filter here, the filter matrix here. But if we work in the joint diagonalization domain, just like we do sometimes, we work in the Fourier transform domain, or we work in the STFT domain. So it's very useful to work in the joint diagonalization domain. So we compute the basis functions from the general eigenvalue decomposition, and then we transform the signals or the problem, both the problems and the filter to that domain. And over there, it's much easier. Why is it easier to work? Why is it easier to work in the transform domain instead of in the original time domain? Why? I repeat, remember we started in the time domain, then we work in the frequency domain. Why we move to the frequency domain? Because maybe in the frequency domain it's easier to separate the signals and the signal subspace, the signals from the noise. So if we are able to separate, to know where is the signal and where is the noise only subspace, it's much easier to find the MVDR, it's much easier to find more accurately the MVDR filter and so on. So we know that there are relations between the filters. So that's why we work also here. So instead of finding the matrix here, the matrix filter in the time domain, we will work in the transform domain. And which transform do we choose? The transform of the generalized eigenvalue decomposition, which I repeat, it's here. You see this matrix. This matrix enables us to separate between the signal subspace and the noise subspace. And then it's much easier to work over there. But in fact, to find this matrix, it requires some computational complexity, and if it's non-stationary signal, then this matrix or this transform changes over time. And sometimes we don't want to work with such complicated transforms, so we simplify it when we work in the Fourier transform domain or some fixed transform. But generally, if we know to separate the signals from the noise, the signal plus noise subspace from the noise only subspace, we know how to separate them, it's better to do it with that transform. As long as we can tolerate the computational complexity. Okay? So instead of working here with linear filtering, we can work in the transform domain. So you see this is in the time domain, multi-channel. So we have X filter desired simply by multiplying the signal X, this vector which contains ML samples, with the matrix and also the noise with this matrix. This is the filtering matrix. We can work in the transform domain. So we can write H as A multiplied with T transpose. This means that instead of finding the matrix H in the time spatial-temporal domain, sometimes we call it spatial-temporal domain, because it contains sensors in the spatial domain and also samples in the time domain. So working with vectors of size ML like this, we call it enhancement in the spatial-temporal domain. Okay? So instead of working in the spatial-temporal domain with a filtering matrix, we transform everything to the signal using this matrix T. And I remind you, this matrix T, the columns of the matrix T are the generalized eigenvectors. And the generalized eigenvectors depend on the correlation matrix Rx and Rv, because it diagonalizes these matrices. That's why we call it the generalized eigenvalue decomposition. So if we know these matrices, which contains a lot of information, and in practice it's very difficult to know these matrices, okay? Sometimes, suppose that we know, we will see some examples that we know, and then we can find this like perfect transform that enables us to separate the signal plus noise subspace from the noise subspace, which is very good. And then instead of deriving the matrix H, we can derive the matrix A and simply multiply it with T transform. Okay, let's continue. So now we will, in order to find the optimal A, the matrix A is the filtering matrix in the transform domain. In order to find the optimal filtering matrix A in the transform domain, we need to define performance measures in the transform domain. And then find the derivative with respect to this filtering matrix and equate it to 0. This is the way. This is the mathematics behind optimization. Okay? So after we learned the single channel, so we are familiar with the mathematical foundations, with mathematical basics, how to do these things. So here it's slightly more complicated because we work with matrices instead of vectors, and we work with additional things. But so maybe the mathematics is a little bit more complicated. That's why it's important to understand the simple things first. But the understanding, the reasoning and understanding, it's the same, okay? Let's continue. So I remind you, we need to find performance measures as a function of the filtering matrix A. So the correlation matrix of the vector Z, we can write it as summation of the correlation matrix of the filter desired. This is the output, the estimate of the filtering after noise reduction. So we have the filtering matrix of the filter desired and the correlation matrix of the residual noise. So you see we can write it explicitly as a function of the matrix filter A, and this contains the eigenvalues, okay? The eigenvalues, the generalized eigenvalues, which we assume that we know. Why we know? Because if we know Rx and Rv, these are ML by ML matrices, long matrices. If we know this information, then we know the generalized eigenvectors, the columns in this matrix. So we know this matrix, the generalized eigenvectors, and we know the generalized eigenvalues. If we know this, we can compute this. So we assume along these derivations that we know Rx, Rv, we know T, so therefore we know T, we can compute T, and we can compute lambda. When we reach the next assignment, so I will give you assignment based on the multi-channel, you will see how to compute T and lambda from these matrices in the example. So you can follow the MATLAB code, how to implement this. Okay, but that's why I want you to understand. And then the derivations in practice by MATLAB code, I will give you so you can follow the steps, how to do it. Okay? First, I want to formulate the problem in the transform domain and to formulate the performance measures in the transform domain. Okay? Performance measures. So the input SNR, in the spatio-temporal domain, it looks like this. You see? trace of Rx1 divided by trace of RV1, which is the input SNR in the reference sensor. This is the input SNR because we would like to see, remember we talked about overview of multi-channel signal processing. We talked about array gain. Can somebody remind me what is array gain? What is array gain? Okay, so improvement of the signal to noise ratio at the output of what we measure, at the output of the array processing compared to the input SNR in the single channel, in the reference sensor, Okay? So this is the array gain. So here, this is the input SNR in the reference sensor, which we denote it as sensor number 1. And this is the output SNR, which is the signal to noise ratio at the output after the matrix filtering, which is the trace of Rx filter desired divided by trace of the noise, residual noise. And we can formulate this output SNR based on the matrix filtering, the filtering matrix, A, and things that we know, lambda, for example. Okay? And here we know Rx1 and RV1, we know them. So if we want to find A, we want to find filtering matrix A such that it will maximize the output SNR, what do we need to do? To take the output SNR, this expression, to find derivative of this expression with regard to A. The only thing we don't know here is A. So if we find the derivative with regard to A and equate it to 0, we will find 8 that maximizes the output SNR. Okay? That's why when we optimize sync, we want to define things, formulate it as a function of A, and everything else we know. We know. We assume that we know. If we don't know, we need to estimate it. Okay. So RZ looked like that. This was before, and this, I think it went down. Okay, so we know that the output SNR is smaller than the lambda 1. Lambda 1 is the largest generalized eigenvalue. So it's the first component in the diagonal here. This is lambda 1. Let's define the noise reduction factor. Noise reduction factor is the trace, is how much noise was in the reference sensor. This is the reference sensor. So the trace of RV1 compared to the noise at the output of the filtering matrix, which is the trace of A transpose. This is the noise reduction. And we want the noise reduction factor to be as large as possible. We can similarly define the desired signal reduction factor, which is what is the trace of Rx1, this is the desired signal in the reference sensor, divided by the power of the filter desired signal, which is the trace of A lambda A transpose. And we get similar expression that the gain in SNR for a matrix filtering A is the ratio between the noise reduction factor and the desired signal reduction factor. we can define the desired signal distortion index. So the desired signal distortion index is the expectation of the error between X filter desired, the desired signal which is estimated, which is given after the matrix filtering, compared to the block, to the vector of samples of the desired signal in the reference sensor. So you see, this vector is what we want to estimate. This is what we get at the output of the matrix filter, but it contains two parts. One is the filter desired and one is the residual noise. So for the distortion, we just look at the difference compared to the filter desired. Just like what we did with the single channel. And we normalize it. We normalize it with a trace of Rx1. So we get distortion. And yeah, the distortion is usually between 0. It's positive, you see? Positive. So it's between 0 and 1. And we want it to be as small as possible. We can define the mean squared error. So the mean squared error, we take into account the error between the output of the filtering matrix, Z, and the samples of the desired signal in the reference sensor. This is the error. And the error contains two components. One component is related to the distortion. The other component is related to the residual noise. And if we take the mean squared error of this, so it contains two components because the noise and the desired signal are uncorrelated. So we get that the mean squared error can be written as two components. One component is related to the MSE-based distortion. The other component is related to the MSE-based residual noise. So we want to minimize both. We want to get as small as possible distortion and as small as possible residual noise. But of course, we cannot, if we try to minimize one, the other one will increase. If we try to minimize the noise, the distortion will increase. One comes at the cost of the other. So the MSE, we try to minimize their summation, their sum. And then we get the Wiener filtering matrix. And if we add here a factor mu, here, what do we get? Trade-off. Exactly. So if we add here mu, we get a trade-off between noise reduction and distortion. If mu is larger than 1, the trade-off filtering matrix will try to reduce more noise, but will get higher distortion. If mu is smaller than 1, it will suppress less noise and will get less distortion. Okay, so this parameter, so we'll see that, you see, even here, when you formulate the problem, already we understand 3 different types of filtering matrices. One filtering matrix is MVDR, which is simple. In the transform domain, we keep the projection in the first P eigenvectors. If we keep these components from the measurement y, we take the measurement y, this vector, and we keep the components in the signal subspace that is spanned by the first P eigenvectors, we suppress the noise-only subspace, we get MVDR. If we take the mean squared error, we try to minimize it, we get the Wiener filtering matrix. If we put here mu, we get the trade-off filtering matrix, and so on. So you see the similarity between what we learned already and how we work with the multi-channel. Okay, but there are some things beyond that, okay? But there are some similarities. I will stress things which are different also. How do we find the Wiener filtering matrix? Okay, so you think, okay, what do we have? We have here an expression, mathematical expression. When you want to find optimal of a function, so you need to write the function that you want to minimize or maximize explicitly as the variable. Here the variable is A, the filtering matrix, and everything else is known. You see here, everything is known. And also, only what is missing is the matrix A. And then you need to find the gradient of JA, the mean squared error as a function of A, with respect to the matrix A. And now you try to find this derivative, but you see trace, you see matrices, and maybe you are not familiar with that, which is fine if you're not familiar with that. That's why I sent you yesterday, some material, how to do derivative of this. And even if you don't have the material I gave you, you can find information on the internet how to do these derivatives, okay? And it's useful because it helps, just like you study integrals and derivatives and so on. So this kind of formula are very useful. Okay, but it's not difficult to estimate or to find the derivative. And we will see how to do that, okay? Maybe it's a good to include this. So when we get the Wiener filtering matrix, so see from the material I gave you or from formula on the internet how to find the derivative of this expression, okay? So it's a good exercise. Okay, so we have functions between the MSC, the ratio, just like we had a single channel. Don't want to go beyond that. Okay, now let's talk about the Wiener filtering matrix. So we need to find the minimization of JA, just like I said. And then the solution is this one. Okay? So try to prove that this is the solution, but don't put the solution in the derivative over there, but try to find the derivative. It's a good exercise, especially if you're not familiar how to do the derivatives or gradients of scalar functions as a function of a matrix. Okay? So it's a good practice. Now we find, so we can write the Wiener filtering matrix this way, because we defined it. This is the Wiener filtering matrix in the transform domain. Now if we want to have it in the spatio-temporal domain, we need to multiply it from the right with the matrix T transpose. So if we open this, we see that we can write it this way. Okay, so let's write it here. So we can write it as the Wiener filtering matrix. We can write it as matrix I, which is defined as identity matrix and all zeros. Okay, so it's defined for Rx summation from I equals to 1 to ML Ti transpose. These are the eigenvectors, generalized eigenvectors the columns in the matrix T. 1 plus lambda I. Very nice. This is a Wiener filter. Wiener filtering matrix. And what we have here, of course we can express the Wiener filtering matrix like this, but I will show you why it is useful over there to write it like that. And then we also see that the Wiener filtering matrix, just like with the single channel, it always improves, or at least does not degrade, is that always you get some gain in SNR, larger or equal to 0. So the output SNR will be not smaller than the input SNR. The more information that we get, the higher signal-to-noise ratio that we get at the output. Let's see an example. Okay, so the assignment today will be to repeat this example. Or maybe I'll give you another one. Okay, but let's understand this problem. So suppose that we have a source signal that comes from a certain direction, and then we have M sensors, uniform linear array, which means that all sensors are on a line, and the distances between the sensors is fixed, is D. And we know the configuration of the array. We know the sensors placements exactly, okay? Suppose that the desired signal, the desired source, transmits a wave, far field, okay? Far field wave that looks like this. A cosine 2 pi f0 t plus phi. A is not known, but A is constant. F0 is the frequency, and phi is random phase uniformly distributed between 0 and 2 pi. And we have additional Gaussian noise. But now, because we have multi-channel, and also we have some thermal noise, but because we work with multiple sensors, we need to know also where the wave, or the source signal and the interference, where they come from. So we assume that the desired source is from the broadside, theta equals to 90 degrees, and interference is from the end fire direction. It's from 0 degrees. And in addition, we have some level of thermal noise. Okay? So we can write this example that each sensor receives a desired signal plus noise. And the noise is a superposition of interference plus thermal noise. So based on this example, we see that the desired signal, because it comes from the broadside, so if we have an array like this, and the desired source comes from 90 degrees, from here. So all the desired signals in all the sensors are the same. Okay? So xi is the signal, the desired signal that is received in sensor number I. So it's the same as the desired signal that is received in the reference sensor. All the same. But for the interference, it's not the same, because the interference, U, it comes from this direction, from the end fire. Theta equals to 0. So if the interference comes from here, so the correlation between samples depends on the delay, how long it takes to propagate from one sensor to another. So you see, this is the relation of a sample T compared to the sample T minus tau in the reference sensor. This is the reference sensor number 1. So if we take sensor number I, so the sensor number I, so sample T is like the sample T minus tau I that was at the first sensor. And this is the time that it takes to propagate from the first sensor to sensor number I. So it's just delay because it propagates from this direction. Okay? Give you a simple example just so you understand. So using this information that we know the direction and so on, we can find these matrices, Rx and Rv. Okay? So how does it look? So I can construct these matrices according to the relations between the signals. So Rx will be Rx1, Kronecker product with a matrix of all ones, because the same signals are received. So I don't want to waste too much time on the derivation. You get it in the assignment. Okay, so you can follow one by one equation and make sure that everything is correct. And also we can find this matrix, Ru, for the interference. And for the thermal noise, what do you think? The thermal noise, what will it be? The matrix, correlation matrix. For the thermal noise, it's totally uncorrelated, because any sample from one sensor is uncorrelated with any sample from another sensor. So it's a diagonal, and if it's the same level of noise, thermal noise, so it's sigma squared of some level, sigma W squared, multiplied with a diagonal matrix, identity matrix. Okay? So here we know all this. You see here, this is the thermal noise, the contribution of the thermal noise. This is the interference. And together we have the correlation matrix of the noise. And then we can compute from these two matrices, we can compute the generalized eigenvectors and the generalized eigenvalues and sort the eigenvalues according in a decreasing order. Okay? We can also compute the input SNR for this specific example. And let's see an example, or specific example with these values. Suppose that A equals to half, F0 is 0.1, the variance of the interference is 0.5, the variance of the thermal noise is 1% compared to interference. So it's low thermal noise. Why do I choose for this example low thermal noise? Because you see, when I use multi-channel sensor array, it works best to reduce noise that comes from a certain direction, directional noise. If the noise is thermal, I still can reduce it by averaging the signals. For example, if I have only thermal noise and the source comes from this direction, so the source comes to all sensors from this direction, so there is no delay. So I can just average these signals. What will I get? Higher SNR. So I can reduce the thermal noise by averaging the signals. But if I have an interference, I can suppress it much better than just averaging. I can suppress it such that I will get some kind of null in that direction, in the beam pattern. We talked about the beam pattern. So I want to reduce beam patterns, so a signal that comes from this direction will be suppressed as much as possible based on the direction. So the filtering matrix takes into account the correlation between samples here and samples in any of the sensors, And based on these correlations, try to minimize the amount of signal that is measured from this direction. Okay? This is what we're trying to do. Okay, so let's see how the Wiener filtering matrix, how it performs as a function of L and the number of sensors. So here we have the gain in SNR, and here we have the minimum mean squared error, which is the MSC by using the Wiener filtering matrix. And as a function of L, and each color corresponds to a different number of sensors, different number M. So the blue is for M equals to 1, which is a single channel. M equals to 2, this is the green, 2 sensors. Here is 5 sensors, and here it's 10 sensors. So what we can observe, that when we increase L, the number of samples that we use for each sensor, or when we increase M, the number of sensors for a fixed L, we increase the number of sensors, we get improved output SNR. We improve the gain in SNR. Very nice. But this is obvious. Even if I ask you, without showing you this example, you would agree, right? When you increase L, or when you increase M, you increase the number of sensors, you increase the samples, you have a longer vector here, because you use more samples from each sensor and you have more sensors, so you use a longer signal, longer vector of measurements. So you use more measurements, so you can estimate better the desired signal. Of course, makes sense. But my question is, what do you think for this specific example? What is more important? To take more temporal samples or to take more sensors? What is more important? Okay, so suppose that this vector, the size of this vector is 20. 20. But I don't tell you what is M and what is L. The size. So the complexity of working with something like that is the same, okay? Size, length, M, the matrices, and so on. Okay, so I can choose 20 samples, L equals to 20, and choose one sensor. So the gain in SNR will be something like that, less than 10 dB. Okay? Or maybe I can take 10 samples, L equals to 10, and 2 sensors. Wow, this is a big jump. The gain in SNR increased to 20 dB. So I can reduce L and increase the number of sensors. So the effect of increasing the number of sensors is much more than taking more samples from each sensor. So increasing L is much more important than increasing L. We want to use more sensors. This is one observation. Another observation, we see that when we take 2 sensors compared to 1 sensor, there is a big jump in the output SNR. But when we increase from 2 to 5, it's less. The jump is less than jump from 1 to 2. Which means, what does it mean? That the significance of additional sensor decreases. The more sensors that we have, the additional of one more sensor is less significant. So the big jump comes when we increase from 1 to 2. Because with 1, we don't have any spatial information. with two sensors, already we add some spatial information. So we can separate between source that comes from certain direction and source that comes from another direction. We have this spatial information. Now, if we add more sensors, the significance of the additional sensor becomes less and less. So here is the jump from 5 sensors to 10 sensors. See? So it decreases. And of course, the MSE decreases, the mean squared error divided by L. Why do we divide the MSE by L? Because we want the average MSE relative to a single sample. Because remember that we estimate a block of L samples. So the MSE that we wrote before is the MSE, the total MSE over all the L samples. So if we want the average MSE per sample, we need to divide it by L. Okay? So we see that the average MSE for each sample reduces when we increase L or when we increase the number of sensors. This is beautiful. But this information, it's a lot. And we assume that we know this information. If this information is incorrect, we will not get these nice plots if the information is incorrect. But it's correct because it's based on the simulated signals. We simulated signal and we computed these matrices from the simulated signals. Okay, that's why we have it. Now, suppose that we choose L equals to 30, and we change the variance of the interference such that we change it from the input SNR from minus 5 dB to 15 dB. Okay? So we plot the gain in SNR, the MSE, the noise reduction factor, the desired signal reduction factor as a function of the input SNR for different number of sensors. The blue is one sensor. This is 2 sensors, 5 sensors, and 10 sensors. Okay, so you see, the more sensors that we use, we're able to reduce more noise. Okay? It makes sense. Why? Because we use more information. If we add more sensors, you see, what is the information that we use? We use, in these matrices, we use the information which is a correlation for any sample in the reference sensor, or actually between any sample in the vector of L samples in one sensor compared to any sample in another sensor within the vector of L samples. So the more information that we use, we add sensors, so we need more information, we use more information, therefore we improve the noise reduction and the output SNR. Regarding the MSE, we are able to reduce the MSE. Regarding the distortion, you see there is a big jump in the distortion, reduction of the distortion, when we jump from one sensor to more than one sensor, 2 or more. You see, there is a big jump. Why? Okay? Why is that? Why the jump is here? You see, because for this example, when we have the desired source, if we have one sensor, in order to reduce noise, we use the filtering, the Wiener filtering matrix. So in order to reduce noise, we need to distort the signal. But even if we have we have two sensors, we can reduce interference. Here the interference is the dominating noise. The thermal noise is relatively low. So even with 2 sensors, we can reduce much of the interference based on its direction without distorting much of the desired signal. So we can actually, what we get is just like some sort of a null to that direction. We can suppress much of the interference even with two sensors. And of course, the more sensors that we use, we can suppress even more noise. But the distortion will be small. Okay, so we don't sacrifice much of the distortion into the noise reduction. Here it will be smaller because we use spatial information, and the interference and noise and desired signal in direction. A question. Suppose that the interference comes from 90 degrees. Both desired signal, interference, both come from 90 degrees. What do you think? If we add more sensors, do we get better performance? No. It doesn't add any information because there is no spatial separation. They come from the same direction. And here it's without any reflections. Okay, if there are different reflections patterns, different impulse response, something else. Okay, but if both are in the far field and come from the same direction, the fact that we use more than one sensor, it's not going to help because we don't have spatial separation. If one is close and one is far, so it's one in near field, one is far field, it's okay. We can add. And then we can use multiple sensors. But if both far field from the same direction, we cannot suppress noise from that direction without sacrifice of the distortion of this desired signal. This is a realization of this example. So this is the noisy signal. The noisy signal is with -5 dB realization. This is an estimate of the desired signal using a single sensor, m equals to 1. This is with m equals to 2, two sensors. You see the big improvement, even two sensors. This is obtained with 5 sensors. Very nice. Using the Wiener filtering matrix. And I didn't use the fact that I didn't try to estimate A and F0, the amplitude of the signal and the frequency and the phase. I only applied the Wiener filtering matrix, but I used this information of A, F0, and the phase. The phase is random, so I don't need it. But I used A and F0 for obtaining Rx in this information. And I also used the direction of an arrival, so I know where it comes from. I use it for Rx, and I use the direction here for RV. Okay, so the assignment is to go carefully. It's very important to go carefully through this example. These figures, 1 to 5, or what we have, 2 to 5? Here, 3. 3, 4, 5. These figures. So follow these figures and the MATLAB code and try to understand. Any question? Play with it. It's important. Okay. Now, because I have this expression, which is a very nice expression for the Wiener filtering matrix, because it's based on some summation. So when I get such an expression, I can ask myself, what if instead of this summation, over all the generalized eigenvectors from 1 to ml, I will take less in the summation from I to Q, something like this. And Q is between 1 and ml. Okay, so if Q in the summation is ML, we get the Wiener filtering matrix. But what happens if I reduce Q? Q will be smaller. What do you think? What will happen? If I reduce Q, do I reduce more noise or less noise? If I take Q smaller, what happens? More noise, exactly. So here I process or I filter all the components in the transform domain, in the generalized transform domain, or joint diagonalization. If here I take smaller summation, only Q in the summation, it means that I take some components and I remove them. Okay, so I suppress them. I put them 0. So H, those components will be 0. So by taking smaller Q, if Q goes down, smaller Q, we're able to increase the noise reduction. But then we pay for that. If we increase noise reduction, we get increased distortion. This is the trade-off. But at least it enables us to find some filters with trade-offs. Okay? So it's possible also to put mu. Remember mu in the... But it's also possible to take this some alternative. So we find other expressions or other filters that enable us to be more flexible with the trade-offs between reduction and distortion. Okay, so it's a nice way. So if we take only one component, the first component, you see Q equals to 1, actually we keep only the one with the highest signal to noise ratio. So this filtering matrix will maximize the signal, the output signal to noise ratio. But this is one form. We will see that we have other forms. Remember that with the maximum SNR filtering, just like the single channel, we have an additional degree of freedom. Over there we had a variable zeta. So also here we have additional degree of freedom. So this, we have actually many possible ways to get filtering matrices that maximize the SNR. So this, if we take Q equals to 1, is one of the solutions, because we see the output SNR is the maximum possible. And but this is the this one is the maximum SNR filtering matrix with minimum MSE. Why? Because we obtained it with the Wiener filtering matrix. And then we take the Wiener filtering matrix and we take only the first component. So it's both the maximum SNR and the free parameter, just like in the single channel, is the one that obtains minimum MSE. So if you take all possible solutions of maximum SNR filtering matrix and you want to find the free variables such that the MSE is minimum, you will get this solution. So I can define this problem, and you need to find the solution. And actually, this is what you get. But we also get it directly from here. Okay? So this is another a nice way. So this is the same or different example. Okay, different example. You can follow also this example. Suppose that we have X that goes like, the correlation goes like this. We have an interference from a certain direction. We have additional thermal noise and so on. So this will be the example. But what I want to show is the effect of changing the value of Q. You see? So this is the gain in SNR, the MSE, the noise reduction factor, and the desired signal reduction factor. So here, this is the blue line for Q as a function of input SNR. The blue line is for Q equals to 1. So you see for Q equals to 1, the gain in SNR is maximal. The green is for Q equals to 2, and then the red is for Q equals to 5, and this cyan color is for Q equals to 9. So you see when you increase Q, you decrease less noise because you increase the dimension of the signal that you keep. So you decrease less noise. So the noise reduction factor decreases. And also the output SNR decreases. But then, when you decrease less noise, you also get less distortion. And vice versa. If you take Q equals to 1, this is the maximum noise reduction. And then the SNR will be maximal, but the MSC will be maximal, and the distortion will be maximal. Any questions? If one element what?
One element doesn't work. If 40 is valid, there's no measurement in that.
So it's not good. One sensor, one of the sensors.
If one sensor doesn't work, so it means that if you choose the reference sensor as the sensor that doesn't work, then you will not get anything. It will be problematic. But if one of the sensors here doesn't work, but you choose the reference sensor, and one of the sensors here doesn't give you any information, then the correlation, in the correlation matrix, you don't have any correlation. So it will not be used. This information is just like taking another sensor, and there is no correlation to the desired signal and no correlation to the noise. So it doesn't affect. It's just like removing, okay? It's just like taking another sensor. Suppose that I have desired source, interference, and one of the sensors is beyond the wall. It doesn't get any one of them. Maybe it gets another noise that is unrelated to this one. So this sensor is not useful. So it will not contribute anything to the performance. Okay? But if you choose that sensor as the reference, then you are not able to estimate. I said choosing the reference sensor, you need to choose wisely. The best sensor, choose it as the reference. And then you try to use the other sensors to help you to improve what you can get beyond single channel. If you choose a bad sensor as the beginning, it's not good. You know? So it's important to choose the best sensor first, as much as you can. If you don't know, choose. You can compare them online and then choose, and then to take. But it's important to choose the reference, of course. Any other question? Okay, so tomorrow we will continue. So we saw something very nice, okay? So go over these MATLAB codes and so on, and also what I gave you before with the speech enhancement. These are beautiful things. And follow the derivations. Tomorrow we will continue with MVDR, control distortion, we will see, and the trade-off. Also something that generalizes all this. So if something is not clear, follow these slides, understand it, and then it will be easy to follow the other derivations. Okay? And tomorrow we will move from the time domain to the frequency domain. So if you are not familiar yet, something you don't understand with single channel, it's important to understand that. You see, after we understand how to do in the single channel, generalization to multi-channel, it's much easier because we understand. When you work in signal processing, it's not like you try to solve something mathematically. It's not working in signal processing. Signal processing, you need to understand the physics behind the measurements, the model, how to combine, and all these derivations. So it's a combination of understanding and the mathematics behind it. Okay? That's why if something is not clear, it's important, because tomorrow we will continue and we will extend the single channel in the frequency domain to the multi-channel, also in the frequency domain. Okay? Thank you. So we'll meet tomorrow. If you have other questions that you want to ask me, you can also ask me now.